webinar on Virtual Beach. Virtual Beach is a decision support tool that facilitates the development of statistical models of water quality at site-specific locations. It allows users to estimate any general response variable, such as microbial or blue-green algae concentrations, using commonly measured environmental data. These modeled water quality estimates can then be used to inform site-based management decisions, such as issuing swimming or shellfish harvesting advisories. Today's webinar will feature a live demonstration of Virtual Beach version 3, which is a desktop PC application using an example data set. And we will discuss how Virtual Beach is used to assist in advisory issuances in the Great Lakes states and to forecast water conditions in states and other recent case study examples. If you have a science question during or following the presentation, please type it into the Q&A window at any time. And once the presentation ends, we will go through as many questions as time allows. You can listen through your computer speakers. Please mute your speakers to cut down on background noise. And we will post the slides from today as well as a recording to our website within 2 weeks. And Erin will type out the URL for our webpage in the chat. At this point, I'm going to turn it over to our presenter today, Dr. Mike Cyterski. Mike is a data scientist in EPA ORD's Center for Environmental Measurement and Modeling. Mike, thank you, and take it away.
Thanks, Lisa. Yeah, welcome everybody. I'm here today to talk about Virtual Beach, and I might reiterate some of the stuff that introductory stuff that Lisa said, but primarily. Oh, my slide is not. Let's see. There we go. Okay, so an outline of what I'll be talking about today. We're going to first give you kind of an overview of what is Virtual Beach and how it works. And then I'm going to do a live demonstration with some data from a beach in Alaska using the current version of Virtual Beach, which is version 3. And then to end the presentation, I'll show some slides about how the new version, which is a web-based version that we're developing, how that works. Okay, so what problem does Virtual Beach address? Well, when you want to make decisions, public health decisions based on water quality, a lot of times it's costly or time consuming to measure the actual microbial concentration or microsystem concentration that you need to manage whether or not you might issue an advisory. So we use statistical models in order to help us predict those things using features, or we call them covariates, that are easier to measure. And you know, the 2000 Beach Act amendment to the Clean Water Act specified that you know, the EPA was to study pathogens and indicators and then issue water quality criteria. The states, the coastal states along, you know, the coast of the ocean and the Great Lakes had 3 years to adopt these water quality standards, and then the EPA provides grants for developing, you know, monitoring and assessment programs of these recreational waters. So Virtual Beach kind of ties into this whole process by allowing you to predict the water quality and hopefully make sound decisions on whether or not to open or close your either beaches or shellfish harvesting sites or even water intake sites. So so this is kind of redundant with some of the stuff that Lisa was saying. Virtual Beach is a decision support tool. It's desktop software. If you don't have a background in statistics, some of this presentation might be a little much. Normally, we have almost like a 2 or 3 day training workshop to walk people through the process of developing these models, and we go into the statistical background. I'll kind of be glossing over that today. This is just simply don't have enough time. It's more of an introductory presentation, but Virtual Beach does use a few different. This is version 3. Uses a few different evaluation methods for creating these statistical models. Linear regression is one, and that's a fairly common one and historically used quite a bit when you're trying to establish a relationship between a dependent variable, like your microbial concentrations, and all of your independent variables, or we call them features or covariates. And those are things listed down below there, like rainfall, antecedent rainfall over the last 24 hours or 48 hours, water temperature, turbidity, wave height, the number of dogs or birds, or even beachgoers. If there's a tributary nearby the beach, maybe the discharge or the turbidity in that tributary. The second evaluation method available in version 3 is a decision tree technique. And again, if you're not familiar with decision trees, I'm not going to spend too much time discussing what those are, but it's kind of a machine learning technique. It's called gradient boosting machines, and they build like a hierarchical decision tree. There's a third called partial least squares regression, but I'm not going to be talking about that one today. And so then the water quality estimates that come out of these models are used for site-based management decisions. So real quick history of Virtual Beach. I've been associated with this program for 10 or 15 years, it seems, probably more like 15. So versions 1, 2, and 3 were developed closely with stakeholders. There were a lot of state beach coordinators and managers, primarily from the Great Lakes states. So we would do training in different sites, maybe once or twice a year. We get lots of feedback from users and try to accommodate their suggestions. The most recent version, version 3, was developed with the help from the USGS Water Science Center in Middleton, Wisconsin. The folks at the USGS Water Science Center in Columbus, Ohio, have been very active users of Virtual Beach. Donna Francie and Amy Brady there have done a great job. They have modeled a lot of beach water quality in Ohio and Pennsylvania, along the Great Lake coast there, beaches there, and they've also begun to model microcystin concentrations for related to harmful algal blooms at public water intake sites. I've done training workshops in South Carolina and North Carolina for state and local shellfish managers who are looking to estimate water quality at these harvesting sites, to know when to open and close those sites. And again, most of the early users of VB were around the Great Lakes states, and it was used to model beach water quality and help them know when to issue swimming advisories. A couple of things that have popped up lately, Dr. Natalie Nelson, who's at NC State, she's in the Department of Environmental Engineering. She is developing this database called Shellbase, which is accumulating all the water quality information for shellfish harvesting sites along the, North Carolina, South Carolina, Georgia, even Florida. So it'll be this big database that hopefully Virtual Beach can synergize with and either pull data in or be set up to use the type of output data sets that Shellbase will be accumulating. And that same type of thing is going on with the Office of Water's new sanitary survey app, which is an application for gathering water quality information at a variety of beach sites. And like I said, I've done training workshops mainly around the Great Lakes and the Atlantic coast, and there's been participants from all over North America. We had a lot of Canadians when we had our training workshops in Ohio. people from Europe and even Guam. So there's been a lot of interest in what essentially is software that, if you're an adept programmer, you can write this code in Python or R, but Virtual Beach is just a nice wrapper that facilitates the modeling, makes it a lot easier. So now I'm going to switch over. I got to stop presenting this screen. I'm going to switch over to first show you what a data file looks like that would be read into Virtual Beach. And then I'll demo version 3, a little bit how it works. So let's see. Okay, so here's the test data set. Hopefully everyone can see this. This is simply a CSV file. We can also import Excel files, but in general, how this is set up is your first column is like an ID column for each observation. This would be historic data that you collected on not only the dependent variable that you want to model. In this case, it's column B, say fecal coliform. And again, this is a site in Alaska that an employee of the state of Alaska sent me, and I was helping her use Virtual Beach, giving her some training. But in this case, they were interested in predicting fecal coliform. And then these other columns C through J, are their features or covariates or predictors. Here it's enterococcus, water temperature, dissolved oxygen, specific conductivity, etc. You can see all these here. But each row represents an observation. So we've got the date here is very typical for people to use as the ID, the date that water sample was collected. We have the fecal coliform measurement, and then we have the other measurements that were taken on that date. So we're going to develop either, like I said, a linear regression model or a gradient boosting model to try to estimate fecal coliform. So when we have these other things, we can estimate fecal coliform. We don't have to measure it directly. And in general, like I was telling her, we don't typically advise using other microbial measures to predict, your dependent variable, because when you go to use this model, it's not any easier, most likely, to measure enterococcus. You're not going to have it. You're not going to know what that value is on that day you go to make a measurement. So these other things, you can go out the morning of, say, 7:30 a.m., 8 a.m., and you can measure water temp or dissolved oxygen, specific you can do that pretty fast and easily. But this enterococcus, you probably have to take a water sample and send it to the lab. So it hasn't really saved you any effort if you're trying to model fecal coliform. But regardless, I'm just going to go ahead and show the model with enterococcus added into it. So here's our data set, and we can see this data set has how many rows? 147 rows. So it's actually a multi-year data set. It's the earliest observations are from 2005, and they go all the way up to 2020. So that's another thing too, is typically you got to be careful in terms of how much historic data you use. If your beach has changed a lot in the last 10 or 15 years, and they've made management practices, or the population has grown a lot, conditions might be very different there across time. You might have different source terms now than you did way back when. And so in general, your models are going to be better if your data set represents a homogeneous period in time where conditions at the beach were fairly similar. That even goes for, like, if one swimming season was a very dry and warm year, and then another year was cold and wet, that could lead to some difficulties in modeling or make it a little more complex. It just depends. The longer the time series you have, the longer the period that you've monitored, what I like to think of it is, the more robust your model is to predict in the future. It's kind of seen it all. If you are just using a short time period, if you only have 1 year data and that year happened to be a very dry, very warm year, and then the next year is a very cold, very wet year, your model might not be as good. But that's it for the data set. I have to close it down so we can open it in VB. I need to stop sharing again. Okay. And now I'm going to share. Okay, so I don't know how instantaneously this happens. Hopefully everybody can see now. This is what the Virtual Beach program looks like when you first open it up. This location mapper is the first thing that pops up. And in general, what we use that for, the main job of this window is for you to mark your site and find the beach orientation. Because one of the features of Virtual Beach is you can turn wind speed and direction into these parallel and perpendicular components to your beach. And those tend to be better predictors than just wind speed and direction alone. So I always go here. I grew up in Erie, Pennsylvania, right on the shores of Lake Erie. And we had we had some nice beaches here along the coast. I'm just going to demonstrate how you measure the beach orientation. So what you can, zoom with your mouse wheel. I zoomed in here. That's how I got here to Erie. And so I can click here. Say if we were modeling, our data came from this stretch of the peninsula here. I can put the cursor there, and then over here I click Add First Beach Marker. And then I click over here. I put Add Second Beach Marker. Then I click somewhere out in the water here to tell it where the water is. And I hit, I click Add Water Marker. And then we can see right here in this pane here, the beach orientation was given to us as, this is more precision than we need, but it's about 245 degrees, 247 degrees. And we could either write that down in our notebook, or Virtual Beach will remember that now. So when we import our data set, if our data set has wind speed and direction, we can turn it into what's called the A component of wind, which is the alongshore component, and the onshore offshore component of wind, which is perpendicular to your beachfront. And those, like I said, tend to be better predictors of water quality than just raw wind speed and direction. So that's kind of the main use of this mapping window here. After we do that and we get our beach orientation, we can go to the Global Datasheet tab, and I'm going to import that data from Alaska that I showed you. And the first thing we need to do is validate our data. So we need to see if there's any missing cells in our data set, or if we have any text in these cells. You're allowed to have text in this first column, which is the ID column. And by default, you can see the second column is blue. So that by default is going to be our dependent variable, the one that we're developing our model for. In this case, it's fecal coliform. Now we can change that if you don't have it. If it's, say, column 5, after we validate, we can change that. But it's just easiest to have it be column 2 because it starts out as the dependent variable. So I'm going to hit this button up here to validate our data. And I'm going to hit scan, and it's going to find down here there is a missing cell. So I can do some things here. I can either type a value in here if I know it. I'll talk about in the newer version of Virtual Beach, we have powerful routines for imputation. Imputation is just estimating missing values from their correlations to all the other values in the data set. But in this version, we don't have that. So in general, what we do is we just delete the row. So we're not going to use this row of data. So I click here and I say delete row. And again, I'm kind of going over this quickly. There's a lot of other features here. Normally this is a 2-day training workshop, but we're just kind of being superficial here. But I'm going to take action and it's going to delete the row, and then it says no anomalous data values found. So we're okay. We can return to the data set. And now we're ready to go. Like I was saying before, say for whatever reason, this column that's dissolved oxygen, if that was our dependent variable, our response variable, we could right click and set it as response variable, but it's not. So I'm going to do this. And for the most part, in my experience, modeling a lot of these data sets, it's nice to have the models tend to work better, especially linear regression, if the concentration is log transformed. A lot of environmental concentrations are log normally distributed, and gradient boosting doesn't care as much about having a normally distributed response variable, but I think it helps with linear regression. But if we want to do that, we can just right click and hit transform log 10, and it'll make the log 10 out of fecal coliform. And then, so once we validate our data, these 3 buttons become enabled. We have compute AO, which, like I was saying, is for alongshore and onshore, offshore. So any data, any type of data that has a speed and a direction can be done in this manner. And typically we have wind, speed and direction, current, speed and direction, and then we can have wave height and a wave direction. So that's kind of a magnitude and direction. So any one of those you can do. And what I need to do here, this data set doesn't have it, but if I had, say, dissolved oxygen was my wind speed, and say this column was my direction, you can see here, down here, it saved the beach angle from the map. It filled it in here, 247, and again, we have a ridiculous amount of precision there. Even like 245 is probably close enough. So we can type that in there. We hit OK, and it'll make 2 new columns, which are the A component and the O component for wind. And so if we had current, speed, and direction, we could do that. And you can see it turned these columns red. It disabled the original wind, speed, and direction. But that was obviously not something for this data set that we needed. So I'm going to delete the columns that I created by right-clicking and choosing delete column. I'm going to re-enable these so they're not turned off. And so that's this button, compute. The manipulate button here, what it is for is if we want to create interaction terms, or maybe say we had 2 different water temperatures and we want to create a new column that's the mean of those 2. It just allows you to create arithmetic expressions of your covariates here. So if we wanted the product of dissolved oxygen and salinity, let's say I can add those over here, choose product, choose add, and then hit OK, and it'll give a new column. So it's pretty amazing. Like, these are simple things in Excel, but Excel is, we found out the hard way, like replicating or duplicating the functionality of Excel takes a lot of coding in your spreadsheet program like this. Our primary programmer, Mike Alvin, who's retiring soon, and I think maybe it's because of the work on Virtual Beach prematurely aged him, trying to replicate all the features in this spreadsheet that Excel. So you don't even think about it when you use Excel. It's so easily done. But anyhow, yeah. So I've added this new column that's the product of these 2, and now we can use this as a potential covariate or feature in our model. And then the last thing, this is more important if you're doing linear regression, we have this transform button. And I guess I'm not going to go over it here, but we could test out all these different transformations of each of our features and find the version of each feature that has its maximum correlation two are dependent variables. So maybe dissolved oxygen would work much better as a predictor if it were the square of dissolved oxygen, or if it were the quad, if it were the fourth root of dissolved oxygen, or the log, or here's a polynomial. So there's a lot of times with biological entities, there might be an like water temperature. They might grow best at an optimum water temperature. It might be a curved relationship where if it's too cold, they don't grow as well, and if it's too hot, they don't grow as well. They have an optimum. So that you might use, you can imagine the relationship between water temperature and the microbial concentrations might look like an upside down U. And if that's the case, then a polynomial can capture that pretty well. So, so like I said, that feature, this transform, just allows you to test out different transformations of these variables to see if it'll help out the model, and we'll find that later. But after you do those things, you can now hit Go to Model, and we get some new tabs that pop up. GBM is the gradient boosting, MLR is multiple linear regression, PLS is partial least squares. I told you I wasn't going to talk too much about that. But so now, we're able to progress to developing a model. So let's look at multiple linear regression first. It has its own kind of local data set, but in general, we're going to keep it the same as the global data sheet. I told you earlier, multiple linear regression cares more about linearity. So on this local MLR data sheet, if we wanted to, we could transform fecal coliform here, and we could look at transformations of all these features on this local data sheet and not change the global data sheet. But in general, I think it's best maybe just to do it on the global data sheet, because GBM doesn't care as much about that. So that's why you might, if you want to look at both, you might do those sorts of things on the MLR local data sheet and not on the global data sheet. And for GBM, the same thing. You wouldn't do those things here on its version of the data sheet. This is GBM's local data sheet. But back on MLR, so here's the data sheet. Now we go to the Model tab, and the first thing we do, this sub-tab here called Variable Selection, we have to tell it what features, what independent variables we want to examine for our modeling. So I'm not going to choose that product I created, but I'm going to add everything else over here. So there's 8 independent variables or features that we want to investigate. And now we hit Control Options, and this is the first thing we need to specify is like, okay, Virtual Beach is kind of like doing a bunch of data mining and saying which models fit the best, which are the best models. But you have to tell it what objective, what criteria, what objective function you want to use to determine what you mean by best. And so there's a lot of different things here. There's something called the Akayaki information criterion, the corrected Akayaki. There's just the plain R squared, adjusted R squared, something called the press residual, which is kind of a one at a time cross validation. There's the Bayes information criterion. So there's model sensitivity. I'm not going to, again, in the training, in the full blown training, we go into more detail into what all these things are. But for now, I'm just going to say, okay, I want to find the model that has the best Bayes information criterion, the BIC. Here is the box where you specify the maximum allowable number of variables in the model, and that depends on how many observations are in your data set. And this is another thing I'm going to kind of gloss over. We go into much more detail in a full-blown training, but here, yeah, you're just saying, say I had 400 covariates in my data set. It depending on how many observations you have, how many rows in your data set, it doesn't make sense to look at a model with all 400. You don't have what's called degrees of freedom. You probably don't have enough degrees of freedom to look at a model with 350 covariates in it. So this is kind of limits the number you can look at. For our data set, we have 145 observations, So we have enough to estimate 8 regression coefficients, which is the maximum number. You know, we have 8 independent variables specified here. But if I didn't want to look at an 8-parameter model, I could set this to something lower, like 6. I'm just going to keep it at 8. This box here is called, this is where you set the variance inflation factor. That's kind of, it tells you how much multicollinearity you'll accept in your model. So that looks at how closely related all your covariates are to one another, all your features are, how highly correlated they are to one another. So every single model that Virtual Beach assesses, it calculates the variance inflation factor, and if it's too high, it says, oh, you know, this model has a couple of features in it that are too highly correlated, so it'll toss it out. So that's kind of how you control that, and you can move this up or down. If you want to be less stringent, you lower this, and if you want to be more stringent, you raise that. I think, yeah. And then I'll talk about these decision criteria and regulatory standard. That's how we're going to make our decisions on when we issue our advisories. They kind of bisect, when you plot model predictions against observations, they kind of bisect that plot and create 4 quadrants for false negatives, false positives, true negatives, and true positives. So I'll show you a little bit of that. In this version 3, there's a couple different things that you can do for this data set in terms of how many models that Virtual Beach is going to evaluate. Here in this data set, there's only 255 possible models, so we can do what's called an exhaustive search, and we can run all combinations of all these different 8 independent variables. We can look at every one covariate model. I should call them features. That's our more correct term that we're using. But every 2-feature model, every 3-feature model, every 4-feature model, etc. But you know, there's some data sets that this number is in the billions or trillions. That there's so many different combinations. And if you have that situation, then we have a genetic algorithm in here that uses the principles of evolution and fitness to kind of get you to a good solution without having to examine all trillion possible combinations. But in this case, we can run the manual because we only have 255. So I hit run. So it's going to look at all 255 models. It's done that quickly. And here, in this box here, it shows you the top 10. And the way that BIC works, the more negative, the better. So this one on top here is the best model. It's only a 2-parameter model. It only has enterocoxy and specific conductivity. So that's what I was saying. It's like typically we probably won't have a model with enterocoxy in it because it won't be easy to measure. But here we can look at model statistics. It's got an R² of about 2.28. We can look at the fitted versus observed map. And here was what I was talking about, where we have a bisection of this map. And the observations are plotted on the x-axis. And here's the regulatory standard. So that's kind of telling you, okay, for observations to the right here, I should issue an advisory. And for observations to the left of this green line, I shouldn't. The blue line is our decision criterion. This is where, depending on what the model tells us, whether we issue an advisory or not. So this is kind of a very important plot that people spend a lot of time on, but you want a lot of observations down here in the lower left, because these are what we call true negatives. So you didn't issue an advisory and you shouldn't have. And up in this quadrant in the upper right are your true positives, where you issued an advisory correctly. Down here, these are false negatives, so you didn't issue an advisory, but these observations are to the right of the green line, so you should have. and up in this quadrant are your false positives where you issued an advisory and you shouldn't have. So you can't move the regulatory standard because that's usually set by law, but we can move this blue line. Once we see our model results, we can move the blue line up and down to see if there's a better place to set the decision criterion in order to issue advisory. So in this case, if we want to lower that blue line, say we say 75, and we lower the blue line, we've pushed more observations up here into the true positive area, but there's no free lunch. That by doing that, we've added more observations into the upper left quadrant, which is false positive. So the more I lower this, I do better. This area over here is termed sensitivity. It's how many your ratio of true positives to all the observations to the right of this green line. And this area over here is called your specificity. It's how well you're doing. It looks at the ratio of observations in this lower left to the total number of observations to the left of this green line. So we see that down here, our specificity using this decision criterion, our specificity is 97%. So we're having 97% success rate over here, but only a 43% sensitivity. So we're only getting 43% right over here. So we could continue to lower this if we want, and we can see as we lower it, the sensitivity goes up. So now it's 0.5, but the specificity goes down. So it's now at 72%. And we can look at a table here. It shows you from decision, and these are log numbers because I logged our fecal coliform. But depending on what we set our decision criterion, this table tells us, okay, when it's very low, we have the best sensitivity of 1, but our specificity is 0. So we have we have a lot of false positives. So we can look down at this table and we can say, oh, here, say, when our decision criterion is 1.6, we have a 64% sensitivity and a 64% specificity. So maybe that is a good decision criterion to pick. And so when the model makes a prediction above 1.6 or thereabouts, we'd issue an advisory. And then we can expect to have, that's an issue that I'll talk about later, is cross-validation. With this version, we do have here, this version 3 has an ability to do some cross-validation. So it'll do what's called a Monte Carlo analysis, and you can hold out some observations and see how the model performs, how this model would perform on observations that it hasn't seen before. And that's kind of how you do it in this version. The next version, the web-based version of Virtual Beach, which I'll talk about next, is heavily focused on that. But I'm running a little bit behind, so I kind of want to end there. GBM is similar. It's just a different type of model. Like I said, it's based on decision trees, and it's nonlinear and highly flexible, so it actually usually does a little better than MLR. And then now that we have this model here, we can go over to the prediction tab. We can use this model now, and like I said, it's only a 2-parameter model. It only has the enterococcus level and the specific conductivity, so we can enter those in here. We could put a date in, and it'll make a new prediction of fecal coliform. We can actually even import a spreadsheet. If we have a whole bunch of these, we can import a spreadsheet and make lots of predictions at once. But again, that's a whirlwind tour of Virtual Beach as it exists in version 3. I'm going to stop sharing, and I'm going to go back to my slideshow. So let's see. So hopefully, did that work? Yeah, I guess it did. Looks like I'm back. So now I want to talk about this new version being developed, which is web-based Virtual Beach, run in a browser. It's got these powerful statistical machine learning techniques, and they're encompassed in what are called these analytical pipelines. But hopefully, it's got a lot of statistical power behind a simple user interface. It'll have private user accounts, so all your, you log in and all your study sites and your data files and the models that you create will be saved online. It's got a heavy emphasis on cross-validation for the assessment of your model's predictive performance. So, we're transitioning to a style where we want to make sure we don't overestimate how well your model is going to do in prediction. So cross-validation is just a term used for, how you subset your training data so that you you get a more valid assessment of how the model will do when you want to use it for prediction. And like I said, there's multiple evaluation methods within these pipelines. There's, again, linear regression, although it's got some more sophisticated nuances to it. There's the gradient boosting, there's support vector, which is another machine learning technique, and somewhat synonymous with that are radial basis functions. And I also want to mention at this point, the person primarily developing this analytical code, he's doing it in Python. His name is Doug Patton, and he's worked a couple years here in Athens. He's an environmental economist and an ORISE fellow, and he's, like I said, developing all these analytical pipelines in Python, doing a great job. And if I misconstrue things or maybe gloss over some details, or if he wants to add any comments, I told him he's free to pipe in and clarify maybe something that I've said. So thanks, Doug, for joining us. So here's a pipeline, and again, I'm running behind, so I'm going to go through these kind of fast. These are the analytical pipelines I was talking to you about in this new version. They start off as a flexible pipeline, and there's 3 functions within a pipeline that are going on. Imputation is just estimating missing values using the other data. And there's a couple different, these blue things over here on the left are all called hyperparameters. And so we have a couple different ways to do imputation. There's K nearest neighbor, and then there's mean value imputation. And then there's feature engineering. This is like how you determine, how you deal with collinearity amongst your features, and maybe how you winnow down your list of covariates. You can use PCA or lasso. And then there's your estimation. So this is going to be different for linear regression. This estimation box will be different depending on whether you're doing linear regression or gradient boosting or support vector machines. But in this case, this is linear regression. There's a couple different alphas that you could potentially use here. So in stage 1, we want to move from a flexible pipeline to a static pipeline. That's what's shown down here. As you go from stage 1 to stage 2, we're going to use what's called inner cross-validation to select which of these hyperparameters are the best for this data set. And so in stage 2 now, we've arrived at a static pipeline where we've determined, okay, KNN worked better, lasso worked better for feature engineering, and an alpha of 0.1 worked best for this parameter estimation. And then we're going to feed the training data back in. And we're going to move from a static pipeline to what's called a model or a fitted pipeline. And in that step, we've used parameter estimation in the training data to do, you can see down in yellow here, this is linear regression. So we've actually estimated the regression coefficients. And now our model is ready to be used for prediction. So this is just a slide Doug and I worked a long time on. I was just kind of proud of it. I wanted to show this is what's going on in that inner cross-validation step, going from a flexible to a static pipeline. You're kind of chopping the data up. And here, in terms of hyperparameters, we've got 8 different combinations of hyperparameters. Each combination is being assessed independently. You're creating all these different divisions of your training data, and here you're assessing which one of these hyperparameter combinations is working best. We can see that down here, this one circled in yellow. So it's this combination here where, okay, mean for imputation, PCA for feature engineering, and an alpha of 0.01 for estimation. So again, oh, here we have it highlighted here, mean, PCA, and alpha of 0.01. So this is for hyperparameter selection within that inner cross validation. So there's two tasks within this web-based virtual beach project. One is to assess your pipeline performance via cross-validation. So that's how we can give you an estimate of how well we expect this model to work when you are going to use it for prediction. And then the second task is to create a final model to actually make the predictions. And these are two separate tasks that don't intertwine. They're kind of independent of one another. If you have a giant data set, a couple thousand observations, you can actually keep some testing data out at the start, and you can directly look at how your final model does at prediction. But in general, with the type of data sets we typically see, you have 100, maybe 150 observations or less. And so that's not always realistic. And so we use this, this step one. We assess the model's performance by using cross-validation. So here's just a slide to quickly show how the training data is chopped up and put into different pipelines. So, you know, our training data is shuffled, all the rows are randomized, and then it's put into, this is 5-fold cross-validation. So we put into 5 folds, each one represents 20% of the training data, and then we make these data groups, 5 data groups, A, B, C, D, and E. Each one is missing one of the folds. So group A is missing fold 5, group B is missing fold 4, and so on. Group E is missing fold 1. So each one is put through this analytical pipeline, and then later on we'll use the fold that wasn't used in order to assess how well the model works. So here in each data group goes into what is the flexible pipeline. We use inner cross validation. Here I have 8 potential static pipelines shown because that's how many combinations of hyperparameters there are, 8 combinations. And so in each case, we say, okay, what was the best static pipeline? Which one did fit the data the best? So in this case, static pipeline A6, here was B2, here was C8, D1, and E5. And then you put that training data group back through this pipeline for your estimation, for your parameter estimation, and it creates a model. So you end up with 5 different models, A, B, C, D, and E. And again, this is still, we're on task 1, which is assessing pipeline performance. And then you take the fold that wasn't in that data group, you put it back through the model to get estimates of your microbial concentrations, and you compare that to the actual concentrations in in this fold, and that allows you to assess performance. You've got 5 different metrics, performance metrics, that you can take an average and see your average performance. So that's, again, all in how the first task is done, which is, give me an estimate of how well you think my model is going to work when it comes to prediction. For task 2, now this is a separate task. We start over from the beginning. We want to develop a model for prediction now. So we put all the training data through a single flexible pipeline that has, again, 8 combinations of all the different hyperparameters. In this example, pipeline 5 turned out to be the best. So we put the training data back through it for parameter estimation, and then that creates a model. And then once you have new feature data, you can use that with that model to create model predictions. Here's just some screenshots of the new version of Virtual Beach, what it'll look like. Here's that location mapper, looks a little fancier. Here's data processing, where you can select, okay, this column is my response variable. Here's the ones I want to look at. Here's the feature columns that I want to look at. It can create, you can specify what rows in the data set you want to examine. We're not going to have probably nearly as many of the spreadsheet manipulation features that we had in the last version. We're going to try to keep it simpler, because I think it's just so much easier to do those things in Excel prior to reading them into VB. It's not worth the thousands of lines of code that it would take us to replicate that. Then this is just setting up your cross-validation parameters over here on the left. Here on the right, you're creating the different pipelines that you want to investigate. So you can say, okay, I want to set up a linear regression pipeline. I want to set up a support vector machine pipeline, and I want to set up a gradient boosting pipeline. And we could, the architecture that we use, it would be easy for us to add other things like neural nets in the future, or whatever sort of evaluation techniques that we want to add, partial least squares regression or what have you. And then we'll have another evaluator called a stacked regressor, which I'm not going to get too much into, but it just kind of gives you a mean prediction based on multiple pipelines. So you can say, okay, let's take the prediction from linear regression, the prediction from the support vector machine, and the prediction from the gradient boosting machine, and let's put them all together and take some sort of weighted mean based on how well they performed. So that's called a stacked regressor, and we'll have that option as well. Then the training dashboard is after you fit your static pipeline, or no, I guess this is, Doug, is this in between stage 1 and 2? Is this your...
No, you would never really see in between the two stages. It's something that's just kind of happens underneath the hood, but to help people understand, what's going on with it.
So are these the results? You could say these are results. We're looking at results from static pipelines here, not models, but static pipelines.
Well, since this would be looking at the results of cross-validation, we're looking at how a pipeline that hasn't seen any data, when you give it data like the data we have, how does it do?
Right.
And
okay.
the principle behind cross-validation, and there's other tools besides cross-validation that do something similar. Cross-validation is the experimental and analytical evidence says it's probably the best way to go. But the principle is you leave some data out from training the model, and then at the end, the way you evaluate the model is how well does it predict on that held out data. For small data sets, holding out data is costly, and so you could repetitively leave out a chunk and cycle through all of your data. And something like fivefold cross-validation can be repeated many times, and so you can even generate a distribution. And the alternative, right, in the world of statistics, is to use a fancy formula that somebody derived with a lot of assumptions. And so this gives us something that's maybe even a bit more tangible.
Thanks, Doug.
Sorry to interrupt, but we do have 5 minutes left. If we could wrap up and move to
okay.
Thanks.
Yeah. So that was actually pretty much the end. So the take-home message is here. Virtual Beach, you use it to create site-specific statistical models for water quality indicators, and that is becoming more general now. People are using for microcystin and at shellfish harvesting sites. So it's really anytime you have any sort of dependent variable that you want to predict using a bunch of features or independent variables. The current desktop version is available through the Virtual Beach SEAM site. The address is given here. The web-based version is currently under development. It should be ready maybe 3 to 4 months before we have a beta version to issue. And there's lots of training materials and support available for Virtual Beach 3. Like I do lots of, I do kind of lots of webinars and in-person training. And so if there's enough interest, I could definitely do a longer version of the training, maybe 2 to 3 hours, and go into more detail. I'm the primary contact for Virtual Beach, and there's my credentials there, my address at the Office of Research and Development. But I do want to mention all the folks working on the development of web-based VB, especially Doug and Darren Smith, Jason, and Brandon are doing lots of the programming work, both the user interface in the back end, and then Kurt Wolf and Raj Beer Parmar are also involved in doing good work. So with that,